cover the chain rule, the last of the big derivative rules. Not that it's the last derivative we'll ever learn, but it's the last technique for differentiation in a certain sense, the last direct technique. Anyway, just a quick review. We've learned the power rule, product rule, quotient rule, trig derivatives. We've learned a whole bunch of different rules, right? Just for some quick practice, let's review. All right, we've got this. Now, if you want to do it a long way, you could say, oh, okay, well, the derivative of f is going to be, right, first of all, this is the same as sine of x times sine of x plus cosine of x times cosine of x. And you can say, well, we could use the product rule. We take the derivative of the first, leave the second alone, plus leave the first alone, take the derivative of the second, and then we do, okay, same thing over here, derivative of the first, leave the second alone, plus the first, derivative of the second, or sorry, plus, yeah, leave the first alone, take the derivative of the second, and we say, oh, I guess that actually cancels out to be 0. Or we could also notice that this just equals 1, and so the derivative of a constant is 0, right? Here, y prime of t, no shortcut for this. This is just kind of messy. We have to use a quotient rule. So we do low d high, and d high is going to be a little bit nasty. I guess I might even move this guy over here, just because we have a product rule within a quotient rule, right? So we do derivative of the first times the second, plus the first times the derivative of the second, plus that guy, right? Just to be clear, this right here is a product rule derivative of this, okay? Okay, so that's low d high minus high d low. Okay, and all of this is over low squared. Okay, don't bother simplifying that. It's gross, right? Anyway, that was a pretty complicated function. It's kind of cool to look back and reflect on the fact that we could take a derivative of such a complicated function, probably more complicated than anything you'd even see in real life. In fact, you could take the derivative of this guy if you wanted, right? It'd be pretty cool, it'd be really cool if you tried to do that, right? But you could, in theory, we could, right? It's just a bunch of products, quotients, powers, whatever, right? And I think that's worth pointing out. In fact, 500 years ago or so, no one knew how to do this stuff. And you know mathematics that the greatest minds in the world didn't know 500 years ago. That's pretty cool. Okay, and now it's time to be humbled a little bit, because if I give you something easy like this, what's the derivative of that? You might be tempted to treat it like it's the square root of x, but it's not the square root of x. So maybe we'll guess. Maybe I'll say dy over dx maybe equals, if we just do the same sort of thing, 1 over 2 root x plus 1, but that's a question mark. We don't know that that's true. Y equals e to the 2x, actually, we do have a clue for this one, because we can rewrite this as y equals e to the x, e to the x. And so dy over dx equals, well, e to the x plus e to the x, e to the x, right? We're doing a product rule, but e to the x, its own derivative. So anyway, we get 2 e to the x, e to the x, which is 2 e to the 2x. Okay, so we actually could do this one. Number 3, we could do that out if we really wanted to. I do not want to spend the time, and we certainly couldn't really do it out if I decided to, do something like that, right? Forget it. And then similarly with this guy, right? Something pretty basic, but again, that 4x plus 7 is kind of messing things up. Now, the question is, why are these functions, these relatively straightforward functions, not something we know how to differentiate? And the answer is because they are compositions of functions, right? So what I mean by that is we're taking one function and we're sticking it inside the other function. Okay? So for example, if we look at the first one, number 1, if we have f of x equals the square root of x and g of x equals x plus 1, then we can write y equals the square root of x plus 1 as the square root of g of x, or f of g of x. See what I did right there? We didn't multiply f and g, we composed them. We plugged g of x into f of x. Okay? So, for example, we did that for number 1. What about number 2? Well, y equals e to the 2x. So we'll let f of x be the outer function, e to the x, and g of x be the inner function, which is 2x. So y equals f of g of x. Okay? And we can do something similar with 3 and 4. Right here, y equals x plus tangent of x to the 500th. So here we're going to let f of x, again, be the outside function, which, be all careful, that's actually x to the 500. Even though 500 comes afterwards, it's still on the outside. And we're going to let g of x equal x plus tangent of x. Okay? So, again, y equals f of g of x. And last but not least, y equals sine 4x plus 7. So we're going to let f of x equal sine of x. And g of x equal 4x plus 7. And so again, y equals f of g of x. So these are all compositions of functions. And so the question is, what is the derivative of f of g of x? Well, it turns out it's this. I should have left it blank. We're going to write it again, because this is important to write. So we'll write this, the derivative of f of g of x equals f prime of g of x times g prime of x. It's actually a pretty compact formula. It's just something you need to get a little used to. Hey, we're not going to prove it. Same sort of thing. Use a limit definition of the derivative. You do some bunch of shenanigans. You get your answer. Okay? So now that we have that, we can differentiate each of these. So we're going to use the chain rule. Oh, and by the way, I should have said this is called the chain rule. Right? We should know that term, chain rule. So now we know dy over dx. Well, in order to find dy over dx, actually, before I write it out, I'll say let f of x equal the square root of x. Let g of x equal x plus 1. And since we're going to be using f prime and g prime, let's write those out too. F prime of x is going to equal 1 over 2 root x. And g prime of x equals 1 over 2 root x plus 1. Or sorry, not x plus 1. Oh my gosh, what am I talking about here? I'm so sorry. G prime of x equals 1. What am I talking about? Okay. So, dy over dx, that's what's going to equal, right? It's going to be f prime 1 over 2 square root of, right? This is the f prime of g of x. See how I just plugged that in? Times g prime of x. And we can clean that up a little bit, right? 1 over 2 root x plus 1. So actually our guess was correct. It did wind up equaling this. Let's look at number 2. Well, we already knew the derivative of this. We knew that dy over dx equals 2 e to the 2x. But let's see if there's another way, maybe an easier way we could do it so we don't have to use the product rule. Well, we know f of x, again, is the outer function, is going to be e to the x. G of x, the inner function, equals 2x. We know f prime of x equals e to the x. We know g prime of x equals 2. So dy over dx equals, so f prime of g of x, right? Because, again, we have f prime of g of x times g prime of x, which simplifies, of course, to 2 e to the 2x. I think that was a little bit quicker, right, than using the product rule. Maybe it actually wasn't because I wrote all this stuff out, but when we get good at the chain rule, we won't even have to write that out. Okay. Now, what about this? And again, I'm going to be mean and make that 500. Right? Now that we know the chain rule, I didn't actually make the problem any more difficult. F of x equals x to the 500. We know how to take the derivative of that. G of x equals x plus tangent of x. F prime of x equals 500, x to the 499. G prime of x equals 1 plus secant squared of x. So f prime of x, or so I should say rather dy over dx, try that a little neater. Okay, there we go. Dy over dx equals f prime all right, see what I did right there? F prime of g of x. Whoop, that was not clear. Tangent of x. All right, again, there's my g of x right there, times g prime of x. All right, and then the last one, try writing out what f, pause the video and try writing out f and g and f prime and g prime. F of x equals sine of x. G of x equals 4x plus 7. F prime of x equals cosine of x. G prime of x equals 4. Dy over dx, just try to write that a little neater, is going to equal f prime of g of x times g prime of x, which is, of course, this. All right, and that's what we've got for this that video.